In this video, I will explain you what is the torque exerted by a magnetic field on a current carrying loop. So I am going to consider a current carrying loop constructed in a rectangular way. So current is entering at this place, and from here the same current goes through this, then through this, then through this, then here, then here. Now this coil is kept in a magnetic field. So for example, I have a coil in this way. Okay, you only have to consider the borders. Now magnetic field is in this way. So when the magnetic field is passing through this current carrying circular coil, what is the net torque developed? So when there is a torque, then this can rotate. So this is basically the working principle of electric motor. But anyway, we will see this. So first we will try to get the value of force exerted by the magnetic field on each conductor. So we have four parts here: AB, BC, CD and AD. So on AB, magnetic field is in this direction. Now force is in this, current is in this direction, magnetic field is in this direction. So force is into. Now what is this? This one is the top view. So this is the magnetic field passing through the coil. Now when I am looking from the top, see when the top, then that looks like this. See, this is BC and this one is the magnetic field lines. Now here it is into, the force is into the plane on AB. Okay, now we will also see the magnetic force exerted on BC. So we have current going in this direction. Okay, magnetic field in this direction. So what will be the direction of force? Direction of force will be this. And I forgot to give you the magnitude of force. What is the value of magnetic force here? Magnitude of magnetic force, FB. So F AB. On AB the force is equal to IL cross B. So but length is perpendicular to this direction. So it will be ILB sin theta, ILB sin 90 is equal to 0. Okay, so here as the length is perpendicular to magnetic field, I can rewrite it as I into L into B. So I into L is L itself, yeah, I into L into B itself. Okay. Now on BC, what will be the value? Here the length is not perpendicular with this. There is an angle of alpha. So that will be FBC is equal to ILB sin alpha. But that is downward direction. Now what is the value of FCD? Current is in this direction. Magnetic field here. So that is coming from the plane. What is the value? Here length and magnetic field is perpendicular to each other. See, perpendicular. Here also perpendicular. What is the value? FCD is equal to ILB sin theta. Sin theta is sin 90. So that will be ILB itself. Current into length of CD into P. But we know that the same magnetic field goes through this one and this one. So magnetic field and even the length is same. Comparing FAB and FCD, we can get a conclusion that the force on each of the conductor is the same, but just opposite direction. Here it is into, here it is coming out. So someone is pushing here, someone is pulling this. But I have to check FAB as well. What is FAD? Force on this. Current is in this direction. Current is in this direction. Magnetic field is in this direction. Yeah. Magnetic field, current, so it will be upward direction. See, magnetic field, then current, yeah, magnetic field, then current is in this direction, yes. So that will be upward direction. What is the value? FAD is equal to I into L into, here also it is the same angle, alpha, here also it is alpha. What is the value? I into L into B into sin alpha, upward direction. So here the value of magnetic force is downward direction ILB sin alpha. Here it is upward direction ILB sin alpha. What will happen? These two forces will get cancelled. See, one is upward and one is downward, and that too along the line. Here it is downward, here it is upward. That will cancel. There won't be net effect due to this. Cancels. What is the reason? FAB is equal to FAD. Now you may ask one question: why these two forces are not cancelled? See, these are not along the line. Here someone pushes, here someone pulls. See, there is distance in between these two forces. So net force will be 0, but there will be net torque. What will happen? This will rotate. See, one pushes with 5 Newton, one pulls with 5 Newton. What will happen? The whole thing will rotate. See, this will rotate in this way. Clear? Now, so we got the value of force. 2 equal forces. So 2 equal force at a distance apart. This is called as coupled. Now how to get the value of coupled? Coupled or torque. Coupled. Both are same. Torque created or coupled is equal to force. Any of the force, that is ILB, into distance in between them. Distance in between these two. I am going to keep as distance. Now the problem here is, see, you can look. Now when you are seeing it from your end, the distance is the width of the book. But when you see at this position, see, this one is one force and this one is other force. Now the distance got reduced. Now if you are seeing the distance in between these two, you can't see that, right? Distance is 0. So distance from maximum, that is coming to 0. So we will see the relation between the distance with different angle. So this one is the top view, right? Now let's say CD, we are going to take a perpendicular to the plane. So always area is a vector quantity, and that vector will be a line that is passing perpendicular to the area. So this is the area, right? Length into breadth is the area. Now this will be the area vector. Now see, as this is the, so this one is the area vector. So on the top view I can see, so top view is, this one is the side view, top view is this one. Okay, same thing. Now with respect to area vector, let's say the magnetic field is making an angle of theta. We have to get the value of this one, right? Distance in between two force. Distance in between two force we need. That is coupled, right? Force into distance between them. If they are equal force, that is how we will get the value of coupled. Now we got force, this one. How to get this distance? This one I need to get. Now I know this one is this. What is that? Width. If this one is width, how to get this distance? Trigonometry. So let's say this one is x. I can get the value of sine theta. Sine theta is equal to opposite. So instead of x I will use d, distance in between them. So opposite by hypotenuse, w. So d is equal to w sine theta. W is width. So for d I am going to substitute this thing. So that will be I into L into B into w sine theta. I am rearranging I into length into width into B sine theta. What is this? Length into width? Length into width is area, right? So I am going to take it as I into area into B into sine theta. Now this is the case for one coil. If there are n number of turns, n, so this is one turn, right? Above this one more turn, then that will be 2 here. So for n turns, torque is equal to multiply. So n I A B sine theta. This is the equation for torque. Now the torque value is different for different angle when theta is equal to 0. So don't get confused here. With respect to what we are measuring theta, see, let's say if magnetic field is passing through this, what is the angle of theta? See, theta we are taking normal to the area. Now if magnetic field is passing like this, the angle in between them is 0. Now if this is the case and magnetic field lines are passing like this, now area you have to take normal to the plane. Now with normal to the plane, this one makes 90 degree. Okay. So that is the difference. So when theta is equal to 0, torque is equal to 0. When theta is equal to 90, torque is equal to maximum, that is NIAB. Don't get confused. This is the plane. If magnetic field lines are passing in this way, that means with respect to area, it is making 90 degree. Okay. Now, if it is in this way, if magnetic field lines are passing in this way, that doesn't mean that these are perpendicular. Area is in this way and magnetic field lines in the same way. So, they are parallel, making torque is equal to 0. This one is very important. Make a note of it. Thank you.